Okay, so yesterday we talked about trig integrals and how if we understand what the 6 trig derivative rules are, which be good to revisit them and make sure we memorize them. We know where the trig integrals are coming from, right? So we know if the derivative of sine is cosine, then therefore the antiderivative of cosine will be sine, right? The antiderivative of sine is negative cosine. So if we understand that we're just moving from the right side of the trig derivatives to the left side of the trig derivatives, that process is the antiderivative, and those are the 6 trig integral rules. Okay. We also talked a little bit about using table of values to approximate areas of rectangles. So we'll definitely revisit that in a little bit. But there's one last topic that I need to do, and that's differential equations. Okay. We'll spend about 20 minutes on this, and then we can start our quiz review. I will have a help session tomorrow morning at 7:30. And then Friday morning, 7:30 as well. Okay, so page 2 and the packet that you just picked up. So differential equations, it sounds complicated, but these are just equations that involve derivatives. So if I have a derivative with an equal sign, that's a trig, that's a differential equation. So steps for solving differential equations. Really, you're just taking the antiderivative, okay? We're going to introduce this topic, but we're really not going to dig into this until the next unit. Okay, so we're just getting a taste of it. Talk about what it is, and get a lot more next lecture. But first thing we do is rewrite y prime as dy dx. It's more, these mean the same thing, but dy dx is just going to be a lot more visually helpful. It indicates to us what variables that we're working with, and also helps us set our sets up our equations a lot more clearly. Okay. Second, we're going to separate the variables on either side of the equation. So what that means is we want everything associated with y on the left side, everything associated with x's on the right side. Okay. And then we're going to take the integral of both sides. Next unit, we're going to see having to work really on both sides of our equation. But here, we're going to just be doing easier ones. So the left side is just going to be the same thing. And the right side is where we just take the antiderivative. Okay, but the more complicated ones require us to work on both sides of the equation, and we'll see that next unit. And then there's going to be a plus c that's going to show up, and we're going to solve for c, finding a specific solution for that differential equation. So we know that plus c indicates that there's a family of functions that all fulfill that that same derivative. But if we're given some initial information, we can help find a c value for that specific equation. Okay, so let's look at example 3 here. Suppose y prime equals 2, solve for y. Okay, so we're sitting at the derivative level, and we're trying to find our way up to the function level. But this is how we can write it in this differential equation form. So first thing is rewrite y prime as dy dx. Okay. It means the same thing, but it just feels that we have more of the things identified for us if we write it as dy dx. Second, we're going to a lot of times we're going to cross multiply. So what that means is if I can find a way to get the y's and x's separated, so if I multiply dx to the other side, I can get my variables separated. So everything associated with the y's on the left side, everything else, including the x's, on the right side. Okay, everybody good so far? We're just algebraically kind of separating. Okay, so now we're going to take the antiderivative of dy. This is at the derivative level. We're trying to make it rise up to the function level. So we're going to take the antiderivative of dy. Okay? And we're going to make both sides rise up to the function level. Now, there's a hidden number in front of dy. What is it? There's a 1. Okay. There's a handout there. Okay. Let's do the right side first. This feels more familiar. If I take the antiderivative of 2, what is 2 going to rise up to become? Good. 2x and then plus c. Good. Now, this one is in relation to y here. So what do you think 1 dy is going to rise up to? But this is in terms of y here. This tells us it's in terms of y. So 1 dy is going to become what? Y. And then y is also going to have its own plus c. Okay. So the dx tells us, okay, this is the x side of things. This side, what dy tells us this is the y side of things. Now, remember how the previous problem I said that if I have a bunch of c's, I can just merge them together? Same thing here. It's not wrong if I did plus c on both sides, but we're just always just going to gather all the c's on just together. And so we just write it as y is equal to 2x plus c. And c is going to represent all the possible positive and negative numbers. So we can kind of just merge it all together and just do plus c. Okay. Some of us are maybe asking, wait, doesn't c cancel out? Well, this c may be different from this c, but 0 is still a constant. So we just say plus c. Okay. So we're just, whether we have multiple terms or both sides of the equation, we're just going to just put everything, all the c's together and just call it plus c. Okay. So this is also what we call a general equation. It's called a general equation because it's not a specific function that you can graph, right? It's a family of functions, right? 2x plus c is going to be all these linear graphs that have a slope of 2, but it may all have different y-intercept. So if the problem asks you for a general differential equation, whatever you do, you're going to just leave that plus c, and that's enough for your answer. Right. Now, when we get down to our specific solution or specific equation, then you're going to be using some additional information to help you solve for c. Right. But let's do another general equation first, and then we can get to a specific differential equation. So dy dx equals x cubed. This is already in terms of dy dx, so there's no need to rewrite y prime. We can just move that dx over to the right side. So I have dy is equal to x cubed. The x, y is on the left, x is on the right. These are both sitting at the derivative level. We're trying to solve it, meaning that we want to make both rise up to the function level. So we're just going to take the antiderivative of both sides. Okay, so again, integral of dy becomes what? Y, because it's really just a 1. So y plus c, but I'm just going to save that plus c for the right side. And then x cubed becomes what if we do power rule? X to the 4th over 4. These numbers always match, and we just say plus c. Okay. Okay, so we're just basically taking the antiderivative. We just have to understand what these notations mean and just do it, take the steps accordingly. Okay, any questions so far? Okay, example 5, solve the differential equation, and then it says solve the specific differential equation. So what we're going to do is we're going to get to the general version first, and then we can worry about the specific. Okay, so even if it asks you for specific, you know that your first step is to get to the general equation, general solution. Okay, so first step, let's rewrite y prime as dy dx. Let's move that dx over to the right side so I can separate my x's and y's. Okay, take the antiderivative. Okay, dy becomes y. Right side, both terms are set up nicely and ready for power rule. Let's do one at a time. 3x becomes 3x squared over 2. Minus 4 becomes a good 4x, right? We have to remind ourselves this is the antiderivative. We don't make that 4 go to a 0. We do if it was derivative, but antiderivative, our degree is going to rise by 1. And then we're also going to include what? Plus c. Okay, I'm going to put a box around this. This is a general solution. But it's asking for specific solutions. So we're going to have to upgrade this to a specific solution. And the way we do that is going to involve that 410. So what do you think? How do you think this 410 can help us? What do you think this can help us find? Yeah, plug in. 4 goes in for x, 10 goes in for y, and that will allow us to solve for what? C. That's it. Okay, so specific solution basically allows us to replace the c with a specific number. Okay, so 10 goes in for y, 4 goes in for x. So I get 16 over 2, which is 8. 8 times 3 is 24. Subtract 8 from both sides, c equals 2. So now that I have my c value, I'm going to write my specific solution. So I'm going to rewrite my general solution, but I'm just going to replace the c with what I found here. Okay, any questions about distinguishing between a general solution and a specific solution? So specific solution takes a little bit more time, but we always have to go through the general solution before we can reach the general. We have to go through a general solution before we can reach the specific solution. Okay, let's do 2 more examples and then we can start our quiz review. So now I want to go through some problems where we may have to work our way up the chain multiple times. So let's say if you think about first semester, okay, first semester, we're able to start from f of x, find the derivative to get us to f prime, and then find the derivative again to get to f double prime. So now if I'm starting at the f double prime level, how can I make my way up to the f of x level? Take the antiderivative, what? How many times? Twice. Yeah, so that's basically it. So if I want to make my way from the second derivative back up to the function level, we didn't know how to do this first semester. Right? First semester, we just knew how to make our way down the derivative chain. And now we can make our way up the chain by taking the antiderivative. But the additional step we have to worry about is that each time we take the antiderivative, it's going to produce a plus what? A plus c. And so each time we go up, we got to worry about having to keep track of a plus c from each process. So each antiderivative is going to produce a plus c. So we have to use that. You know, if we want to find a specific solution, we're going to have to keep track of this process and solve for c along the way. So we're going to have to solve for c twice. Okay, if we want to find the antiderivative twice to get up to the function level. Okay, so now I'm going to be flip-flopping between notations. So just to kind of let you know here. It says to help distinguish between the different plus c's is use plus c to for the first constant and use plus k for the second constant. I realize sometimes that may be more confusing, so it's up to you. If you want to do plus c and plus k, you can, or you can say plus c sub 1 and plus c sub 2 to distinguish between the c's, as long as you can find a way to distinguish the because the plus c is going to be different across the different antiderivative. So we should have to distinguish it. Okay, so let's say we're starting off with f double prime. Okay, if I want to find the antiderivative of f double prime, it's going to make it rise up to what? Up to f prime, right? So f prime is going to be the antiderivative of 6x plus 4 dx. I haven't done the calculus yet, but I'm indicating what I want to do. I know that if I take the antiderivative of this expression, it's going to make this turn into the f prime function. Okay, does that make sense? Okay. So now let's resolve the right side. Okay. And we know that once we resolve the right side, the notation goes away because there's no need to indicate that we want to do something if we've already done it. Okay, so 6x becomes what? Okay, 6x squared over 2, which reduces, I'll do that later, plus 4x plus c. Okay, I'm going to just leave it as plus c, and I'll call the second one c sub 2. Okay. Okay, do some cleanup here. F prime is equal to 3x squared plus 4x plus c. Now, do I have something at the derivative level that can help me solve for c? Is something given to us that we can use? Yep, we have a order pair at the derivative level, right? So that means this I can replace 0, I can plug in for x, and 3 I can plug in for f prime, right? This is like the slope, right? This is my slope value, this is my x value. So I can use my 0, 3, because these are both at the first derivative level to help me solve for c. Okay, so 3 goes in for f prime. Okay, the zeros are nice because c is just equal to what? 3. Now, once you find your c value, go ahead and update your f prime so that we can prepare ourselves for the next level up. Okay, so we're halfway there, but we're trying to make our way up to what? F of x, right? So that means if I want to rise up to f of x, I need to take the antiderivative of this expression. Okay, so I haven't done it yet, but I'm indicating what I want to do, right? I want to, these notations indicates that, okay, I want to make it rise up, make this rise up to the function level, because then I can make these two equivalent. All right, so power rule again, 3x squared becomes, yep, over 3. 4x becomes, 3 becomes, and then this is also going to produce its own plus c. I'm going to call this c sub 2 to indicate this is a different c value. Do some cleanup. Now, do we have something at the function level that can help us solve for c at this level? Yes, order pair 1, 5, right? 1, 5 is at the same level as this f of x. Plug in 5 for f of x, 1 in for x, and then solve for c. So 5 goes in for f of x, 1 goes in for x, 1 plus 2 plus 3 is 6. 5 equals 6 plus, okay, sorry, my key I used k, but you could use c sub 2. C sub 2 equals -1. And then now you can update your function with the new c sub 2 value. Okay, any questions? Okay, let me do example 7 real quick here. Example 7. Okay, so now same idea. We want to move our way from G double prime back up to G of X. But let me change the instruction here. Let me say find G of X, but find the general solution for G of X. Okay. So what that means is we're going to take the antiderivative twice, but we're not going to have to worry about replacing them with numeric values. Okay, so G double prime is 12x plus 6. I want to make both sides rise up to the G prime level because I have to get the G prime before I can get the G of X. So I know my G double prime will rise up to G prime, and then the right side, I'm just going to prepare the notation for it to indicate that, okay, I do want to take the antiderivative. And once that process is done, my resulting expression will be at the G prime level. Okay, so technically this is at the G prime level, but we haven't resolved it because there's that notation that we can't quite get it to where we can play with it. Okay, so let's make it transform up to the the derivative level. So 12x becomes square root of 2 plus 6x plus c. So because we're asking for the most general solution, we're not going to be able to resolve this plus c. We're going to hold on to that c along the way. Now, c is a constant, right? So pretend like treat c like you would if it was a 5 or 6 or -1 or 4, okay? So treat it that way. Okay, so we're going to make it rise up to the G of X level. So before I do that, I just want to indicate what I'm about to do on the right side. I'm going to make it go through the antiderivative process. Okay, so now I'm ready. 6x squared becomes cubed over 3. Okay, 6x becomes squared over 2. Good. Now, c, what is c going to become? cx. Good. cx, right? Pretend like this was a 5, right? 5 would become 5x. 8 will become 8x. -1 will become -1x. Same thing, right? A constant is going to rise up to the first degree level. But this process is also going to produce its own what? So I'm going to have to say plus c sub 2. Right? This c was from the previous antiderivative, and this c is for the current one, right? We did it on the previous one. We just were able to resolve the first plus c before we got to the second one. So that's why we didn't see that one show up. Right? But here, we are asking for the most general solution, so we're going to have to hold on to all of our plus c's. Okay, so here's my equation here after I clean this up. Okay, if you can turn to page 5. Page 5, I want to go through a bit of, this is kind of like basically like quiz review here, but I want us to practice a bit more with table of values. So we talked a little bit about this yesterday, right? Table of values. Okay. So let me go down and try part C. Okay, I want to do part C and D, and then we can start the full quiz review. So for part C, it says, oops, my bad, page 5. So for C, I'm going to use the table above, and for D, I'm going to use the table above. For part C, it says use left-handed rectangles to approximate the area with 3 subintervals from 0 to 9. Okay, so we talked about how rectangles, okay, is going to be width times height. We want 3 subintervals, but again, with table of values, we never want to do this. We never want to use this width equals b minus a over n. Okay, it's not. It's good for functions that where we can find the width, but here the width is predefined, so we're not going to create our own width for our rectangles. Okay, so never use this formula for your table of values. Okay, 3 subintervals from 0 to 9. That means we're only going to go from here to here. Okay, but we want to be able to split these up into 3 subintervals, and each subinterval is going to span across the same number of order pairs. They may not be the same width, but they will span across the same order pairs. So that means each subinterval is going to see how many order pairs? 2. Okay, we're going to go from the middle of the first order pair to the middle of the last of the next order pair. Okay, that's my first subinterval. My second subinterval is from 5 to 8. My third subinterval from 8 to 9. Okay, the width is going to come from your first row. Your height is going to come from your second row. To find the width, what do we do to find the width? Do we add or do we subtract? Subtract, right? So the distance from 0 to 5 is 5 minus 0, which is 5. Okay. The distance from 5 to 8 is 3. The distance from 8 to 9 is 1. So these will act as the width of these rectangles. And then for each subinterval, you're just going to pick off the height that you want. And the height is just going to be the numbers that you see below. You're not going to do anything with these numbers here. You're not going to find the average. You're just going to pick off the correct one and go with it. But it wants left-handed rectangles. So for the first subinterval, what do we want to choose, the 4 or the 2? The 4, because 4 is on the left side. So that's going to be the height of your first rectangle. 5 times 4 is the area of your first rectangle. Second rectangle, we want to choose a height of 2. And third rectangle, you would choose a height of 3. Okay, width times height, area of rectangles, right? So area first rectangle is 5 times 4. Second rectangle is 3 times 2. Third rectangle is 1 times 3. Add those up. Okay, I want to do a trapezoid here because we haven't talked about that yet. Now with trapezoid, we can't do this with trapezoids, okay? We're not going to be able to factor the width out and double all the heights because the width is not the same, and we can't merge all the heights together. So we're not going to be able to do this formula, okay? Instead, we're going to have to do the area for each trapezoid. And each trapezoid is only going to require 2 heights. Okay. 1/2 width, height 1 plus height 2. Okay. So however many trapezoids there are in the table of values, you're going to have to do this however many times we want to find areas of rectangle. Oh, sorry, areas of trapezoids. Okay. So use trapezoids to approximate the area with 2 subintervals from 0 to 20. So this means that we're going to have to add 2 areas of trapezoids together. Okay, so let's span across 2 subintervals. We want it to see the same number of order pairs. So if I want to go from 0 to 20, what's my first interval going to go to? Okay, spans across 4 order pairs, right? And then the second one should also be 4 order pairs, and that is true. So from 9 to 20. Now you see where these brackets are pointing. those are the only y values you're going to touch. Okay, you're not going to touch any of these middle y values because every trapezoid is only going to use the heights at the end, and it's only going to use 2 of them. Okay, we're not going to use multiple like previously, because before we were adding a bunch of trapezoids together, and we're able to merge them because they all share the same width. But here, we're most likely not going to have the same width. Okay, what's the width of my first trapezoid? 9, because the distance from 0 to 9 is 9. 9 minus 0 is 9. Right? What's the width of my second interval? 11. 20 minus 9. I see some students, they want to add these numbers together. They say 29, but we want to find the distance between these 2 points. Okay, so 11. So what is the height that we would choose for the first trapezoid? The 4 and the what? Good. So we're only using the ones at the ends. Okay, height 1, height 2. And then the second trapezoid will only use a height of 7 and that. Good. So we'll just go through this formula twice. 1/2 width times height 1 plus height 2. This is the area of my first trapezoid. Okay, does everybody see that? 1/2 width, height 1 plus height 2. Second trapezoid, 1/2 times what? Width is 11. Okay, height 1 plus height 2, so therefore 7 plus 10. Okay. And the rest you can just use your calculator to resolve that. Ends up being 143. So I'm hoping that you guys feel this is an easy process. However, having said that, because we've done different things with different setups, we may get thrown off. Either sometimes we use the width formula, or we end up adding the width to get that number, or we pick off the wrong height, or we try to do too much with the height, or we try to involve too much with the height for trapezoids. So a lot of room for mistakes, but I think once you get it, you're going to get it, and we'll be able to carry this through all the way until AP review, because this is going to show up. It's a very common way of presenting problems on AP exam. Yeah, on the quiz. Yeah. Okay, so let's begin a portion of the quiz review just to kind of show some of the problems that I'm going to do, and then the problems that we don't finish, I can cover in the help session, but we're also going to be able to do in class tomorrow. Okay, so the first one is easy. You're going to find the sum, but you're not going to use the sigma formula because it's just how many terms are we adding together here? We're going from 2 to 4. Yeah, so, well, we're starting at 2, and then we're going to plug in 3, and then we're going to plug in 4. Okay, so this 4, does that 4 mean that we're going to have 4 separate terms? It means that this is the last value that we plug in, right? So we're only going to have 3 terms, because 2 is going to present 1 term, then 3, and then we're going to stop at 4 because 4 is the largest I value that we find. Okay, so there's no need to have to go through any fancy formula. We just have to go through and plug in and add up the values. Okay, so let's start with 2. After I replace all the I values with 2, I'm going to put a plus, then I'm going to move up to 3. And then finally move up to 4. use our calculator, and we just total those values up, and that gives us 59. And I have the keys attached in your packet. So that should be easy, right? You're just inserting numbers in, and on the quiz there'll only be a few terms, so you should be able to, not have to go through a whole lot of hassle to try to get down to their sum. Right. Now, number 2 is going the other direction, where I give you a bunch of terms added together and asking you to create a rule that will represent that sum. Okay, so we're basically starting here and trying to create a rule with a I value and an upper bound and an expression. Okay, so use sigma notation to write the sum for 2 over cube root of 5 minus 2, 5 minus 4, 5 minus 6, 5 minus 8. So it looks complicated, but you're always going to set up this way. You're going to start with your sigma notation. We'll say I equals, I'm going to always have you start at I equals 1. Okay. And then write down the rule, write down the expression that is not changing. Okay. So what's not changing across all these terms? What's staying the same? The cube root and the 5 and the denominator, right? So I'll put in the minus. Okay. Everything else is going to have to involve some sort of a I to help build this engine. So I want to find a way where if I plug I equals 1 into an expression, it'll produce this. If I plug I equals 2 into an expression, it'll produce this. I equals 3 will produce this, and I equals 4 will produce this. So is there something that I can create up here that will produce, if I plug in a 1, it'll give me 2. If I plug in 2, I'll give me 4. 3, I'll give me 6, and 4 will give me 8. 2i. Okay, let's see if that works, right? So 2 times 1 is 2, that works. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. Okay. Is the pattern below the same? Yeah, so I can also replace that with 2i. So the most common patterns you're going to see is going to involve some sort of exponent or something like this, right? Something, if you're trying to play with patterns, play with exponents, either with the bottom being the variable or the bottom being the base. Okay, so we're going to get some more practice with that. Okay. Okay, let's see if we can do 1 or 2 more. Oh wait, something I missed. Sorry. Sorry. What was your question? I could, but then it feels messier, because if this is I equals 2, then this must be I equals 3. And if I want I equals 3 to give me 4, I'm going to have to do some more. It's going to take a little bit longer, right? So here's the thing, right? If I did, you mean I keep the same expression but start at 2? Okay. What would your rule be? Would you just have I up top? Yeah. So the problem is that if I plug in 2, yes, it'll give me my first term. But then what happens if I increase that to 3? Will that give me my second term? Yeah. So so I think you brought up a good point in the sense that if something works for the first few terms, you have to test it. Okay. So that's something that I did. Now what I didn't point out is make sure you test your rule, because it may work for some of them, but it may not work for all of them. So go through, and it's a trial and error thing. So if it works for the first one, make sure it works for all of them. And something else that I left off is this is the last term. So what should be going up here? 4. Okay, so you brought up a good point. If it works for one, it may not work for all of them. So if something doesn't quite work, then. But I think on the quiz I will have one that starts with 1, so it makes it easier for you to find that property. Okay. Number 3, it says use 3 middle rectangles to approximate the area bounded by the function x squared plus 3, the x-axis, 1, and 6. So all you need to know about this is that this is the function, that's your a, and this is your b value. This is not a table of values, so I have to use this b minus a over n. If I give you a table of values, you're not going to use it, but if I just give you a function and you're asked to create your subintervals on your own, you're going to have to go through this width formula. Okay. All right, let's find the width first. What's my a, b, and n value? Okay. 1 is my a, x6 is my b, and n is what? 3. Okay. So width is 6 minus 1 over 3. Okay. What's my width? 5/3. Okay, so let's build our intervals here. You're going to start at what? What's your left endpoint? 1, okay. Plus 5/3, okay. You'll have your calculator, but let's do this by hand for now. 3 over 3 plus 5/3 is 8/3. Plus 5 over 3 is 13/3. Plus 5 over 3 is 18/3, which is 6. Okay. And can we stop there? Yes, we have our endpoints. But it's not asking for left and right, it's asking for the middle. So we have to find something between these two values. Right. So how do I find what's between 1 and 8/3? Find the average, right? How do you find the average of two numbers? Add them and divide by 2, right? So if you, in your calculator, do 1 plus 8/3, which is 11/3 divided by 2 will give you 11/6. 8/3 plus 13/3 divided by 2. Give you 21/6. So again, you're just averaging the two numbers and dividing by 2. And then between 13 and 18, this will give me 31/6. So these are the x values we want to connect to the graph to use as heights. Okay. So it says use 3 middle rectangles. So I'm just going to find the width and height for each of my rectangles. Each rectangle has a width of what? 5/3. Okay. So my area is going to be 5/3 times f of 11/6. This is my width. This is the midpoint that I'm going to extend to the graph to let that represent the height of my first rectangle. Second rectangle, 5/3 f of what? Yeah, 21/6. And then 5/3 f of 31/6. Okay, so how can I find the specific y values at this point? Plug into the function, yeah. So you're going to just make the calculator do a lot of the work for you. Okay, ends up giving us 6.366 for the first height. The second rectangle is going to have a height of 15.25. Third rectangle, 29.69. And then add that all together, we get 85.509. Okay, we did the table of values, so that should go quickly. We still have to do the limit definition. That's gonna be part of your quiz, power rule, and those differential equations, or having to make our way from f double prime up to f of x. So I'll have a help session tomorrow morning at 7:30. I'm not going to assign homework. I just want you guys to see if you can spend some time working through some of these problems. I have a review worksheet 2 and a review worksheet 3. So we'll finish 1, start 2 tomorrow, and then Friday morning I'll do worksheet 3 as your quiz review. Okay, don't forget your phones.
Raymond, so this is full plate.
Okay.
This full plate. This one. And
Two.
then I have it.
And you have to open one as well.
It's all the same. There was like Thursdays and Fridays.
But Friday's also, okay, but then Mondays, we could do Mondays somewhere. Well, Mondays was Powell, the Powell,
Oh, yeah.
we haven't done that, okay, so you should have. Yeah, tomorrow I'm not gonna go.
Oh, and also, I'm not here tomorrow. So, is there any more?
Oh, you mean like, oh, you won't be there at 5 a.m. We're just gonna work through worksheets 1 and 2 in the packet, and the key is attached. All right.
So this is another version of this. And then also, I was like, that's a perfect, yeah. Yeah, it's short. But we
Yes.
have a web on.
Not gonna speak about
About other goals there. We should do like, is there ever, so like, everywhere it gives us something that needs to draw a line. And the time, I was thinking like,
I'm not gonna.
you have like. You go to lunch or something. Yeah, like, yeah.
So,
Yeah. I didn't decide how we want to be big and.
this, I just.
Like, do you think it would be like too much to be?
3.
It's like-
Differential equation. Just take the answer.
It doesn't look like a calculator. Or not a calculator. Yeah. It's like calculator.
You still have questions, you can.
Is it on the mic?
No, I'll share with the video is.
I feel like that would be like really. I started bringing 2 water bottles because I drink